All right. So 2.3, is all about compositions of functions. So in 2.2, we did algebra functions. That's where we learned how to add, subtract, multiply, and divide our functions. Today with composition of functions, what we're doing is we're taking a whole function and shoving it into another function. So it's a little bit different because we're not doing an algebra that we're used to. Instead, we're kind of doing a substitution. So the composition of a function f with g is denoted by a little circle in between there that we read it f of g, and is defined by f of g of x is the same thing as f of g of x. Like, they're read the exact same way. But I kind of like this format on the right better, because what it's showing you is that instead of x, we're taking the whole function of g of x and sticking it inside of our f of x function. So we're going to plug the whole function in there. And so I kind of like that denotion a little bit better, but we will use both as we move throughout. Finding the domain of our composite functions can be a little bit tricky. We won't do a ton of them just because they're a little tricky, but they're not impossible. The domain of your f of g function, or your composite function, is the set of all x such that x is in the domain of the g function, and then the outputs of your g function are in the domain of f. So your inputs are in the domain of g, and then your outputs of g are in the domain of f. Another way of thinking about it is that if we take the domain of g, which we can find out by looking at the original equation, and we intersect that with the domain of f of g. That doesn't look right. I feel like that's a typo. I feel like it's intersected with the domain of maybe it is right. We'll figure it out. I feel like it's right, but it looks weird. Just know that we will walk through the domain problems as we get to them. I think finding the domain of a composite function and writing out the steps to how we do it is way more complicated than actually doing it when we see an actual example. So here's our example. It says given f of x is 2x minus 5 and g of x is x squared minus 3x plus 8, we need to find some information. And the first thing we're going to find is we're going to find f of g of x. So f of g of x, and I'm going to write it the other way, right next to it, where it's f of g of x. Because what I want you to see is we are going to take the g of x function and we are going to put that in the f function anywhere that there is an x. Because remember, this is like seeing f of x. Well, f of x is 2x minus 5. But instead of writing x, I'm going to write g of x. Let me show you. I'm going to even write this second step. You don't have to write this step. But instead of writing x, I'm going to write g of x. So I wrote the f of x function, but I put g of x in there. You don't have to do this step, but if it helps you to understand what we're going to do, then do it. Because now what I'm going to do is instead of writing g of x like this, I'm going to write out that whole function that they told us it was. G of x is x squared minus 3x plus 8. And then I still have the minus 5 that comes from my f of x. So I'm substituting that g of x in place of the x. Then I'm going to distribute so that I have 2x squared minus 6x plus 16 minus 5. Oh, thank you. And then I will combine my like terms because I have a 16 minus 5. So I get 2x squared minus 6x plus 11. And at that point, I can't go any further. Remember, for these, when they ask us for it in terms of x, you're going to get an output that has x's in it. Questions on what I did there? how I substituted that in. Okay. The second one we're going to do is g of f of x. So instead of taking the g of x function and plugging it into f, I'm going to take the f of x function and plug it into g. So our g of x function said x squared, but I'm not going to do x squared. I'm going to do f of x squared minus 3 times f of x plus 8. So you're going to get really good with foiling and factoring and all that jazz in this section. Whoops. I don't know what I'm doing. Yeah, I was like, I don't know what I'm doing. Don't look at that line. That line's all magic. There we go. Don't look at that. I don't know what I'm doing. Well, now you can't. I scribbled it out. I was like, that seems exceptionally harder than I remember it being. And that's why, because this is a much nicer equation. Yep. Thank you. What shines on the wall is different than what shines on my screen. So yes, please let me know if I'm not on the screen.
Whenever we write it out, do we have to put the squared, or can we do like double that?
Well, I'm going to write it doubled in just a second.
Oh,
so,
okay.
yeah, whichever way you prefer it. Just like you don't have to necessarily write this bit up here if you don't want to. Okay. I'm just doing that right now because this is, I'm assuming, it would be somebody's first time maybe of seeing it written like this, and so I just want to show you where exactly we're plugging things in. Okay. I usually go straight here, and then I would write it on the next step. I would write 2x minus 5 times 2x minus 5 because I know I'm going to have to FOIL it, and it's a lot easier to FOIL when they're written side by side. Okay. And I would go ahead and distribute on that step this negative 3 so that it's negative 6x, and negative 3 times a negative 5 will give me a positive 15. Remember, when you distribute, the sign in front of the number that you're distributing goes with that sign. So we didn't just distribute 3, we distributed negative 3. And then you have to FOIL the 2x minus 5 so that you have 4x squared. And then I would have minus 10x, which would give me a minus 20x. Negative 5 times negative 5 would give me a positive 25. Minus 6x plus 23. I did like an extra step all in one because I did the minus 10x minus 10x, and I just combined it. 4x squared. Then I have minus 20x minus 6x minus 26x plus 48. Tell me if I'm wrong. Let's see if that matches what I have here. And it matches there. So something that's super important to notice is that f of g of x does not equal g of f of x most of the time. And that's because the functions that you're starting with are different. And so when you plug them into each other, you get out different answers. And notice that the first two examples, we had both of these in terms of x. The next example that you can kind of see says f of x of 7. And so instead of having it in terms of x, we're going to have it in terms of 7. And there's actually two different ways you can go about this. If you've already figured out what f of g of x is, which we did, that was the first thing we did, then all we have to do now is plug in 7 for the x and compute out what number that is. So that's not too bad. That's how I'm going to do it first, and I'll show you the other way we can do it. So instead of 2x squared, I have 2 times 7 squared minus 6 times 7 plus 11. Remember your PEMDAS, where you do your exponents first. Bloop. 2 times 49, 98. So when they ask you for it in terms of a number, you should get out a single number at the end. When they asked it for us in terms of x, we got out a expression that had an x in it. And most of the time, they will have you do it in these different steps like we're doing here, where we found f of g of x first, and then in a few minutes they'll ask you for f of g of some number. So you don't have to completely reconfigure what f of g was because you've already found that out. But let's say on a homework assignment or a quiz, it only asked you for f of g of 7. You could do the process that we did first where we found f of g of x and then substituted in. That's totally fine. Or you could do it like this. I'm going to show you, this is like a little star note, I guess, like a bonus note. Let me make sure I'm on the screen. If I have f of g of 7, and I'm assuming I haven't found f of g of x yet. That's my assumption. I haven't found it. What this is saying is I have f of g of 7. Well, I can find g of 7. All I have to do is plug in a 7 into my g of x function. Well, g of x said x squared, so that'll be 7 squared, minus 3 times x, which will be 3 times 7, plus 8. That gives me 49 minus 21 plus 8, which gives me 28 plus 8. And if my math is wrong, let me know. I'm doing this off the top of my head. So I found that g of 7 is 36. But I need to find f of g of 7. So that means I'm really finding f of 36. Well, my f of x function was the 2x minus 5. So f of 36 would be 2 times 36 minus 5, which is 72 minus 5, which is 67. Which is exactly what we got doing it the other way up here. Some students like finding this and then finding this because then you're dealing with only numbers and you're not dealing with the exponents, you're not dealing with the variables at all. I would say almost always, though, you are asked to find f of g of x first. And so then just plugging in whatever that value is into the f of g of x makes sense to do that. But this is the other way that you do it. You find the g of whatever it is first, and then you plug what you get there, that output, into the f of x function and come up with the other output, which is your final answer. Does that make sense? Are there questions on that? Okay, that was like a bonus one. We're going to do g of f of 7 and g of 1. Because you can plug the same function into itself. I will go ahead and tell you we won't do that much. And we had already found, I'll write over here, g of x, g of f of x. We already found what that was. That was our big O long one that we just did up here, which was 4x squared minus 26x plus 48. So when we are finding g of f of 7, we're going to plug 7 in anywhere that there's an x. We're going to get some nice big numbers. Because you're going to have 4 times 49. minus 26 times 7 is 182. 4 times 49 is 196, and minus 182 plus 48 will give me a minus 134, which equals 62. Now for the g of 1, nowhere did they ask you to find g of x. So that's where I'm going to use that other method that I just showed you, where I'm going to find g of 1 first, and then I'm going to plug that into g again and see what I get out. So g of 1, we would plug 1 into that x squared minus 3x plus 8, which would be 1 squared minus 3 times 1, which is 3, plus 8. 1 plus 5, which equals 6. Sorry. So then instead of saying g of 1, I'm going to put a 6 in. So I'm going to find g of 6. 6 squared minus 3 times 6 plus 8. Sorry, it says plus 8. 36 minus 18 plus 8. 26. Questions on any of those that we did? Either method, where we find the f of g of something and then we plug in the numerator, the number, or where we plug in the number to get started with and then we plug in the answer that we get back in.
So
What's
what's the purpose of the last one?
the purpose of the last one?
Yeah, like, what does it mean? So it says g of 1 equals g of 6. So, like, what does that mean?
It means it's kind of like running things through a machine, is how I always think of composite functions. Is you have these different machines. And so in this last case, we're only dealing with one machine, but we're going to run different things through it. So the first thing we're going to run through our machine is we're going to run through the number 1. And when we run through the number 1 through our machine, we get out a number 6. But that's not what we wanted. We want to know what happens then when we stick that number 6 through our machine. And so we have to run it through the same machine again and see what we get out the next time.
Oh, okay.
Does that make a little bit more sense?
When I was looking at it on the screen and looking at it up there, I was getting like, expression. Like I was looking at it as g of 1 equals g of x or 6.
Oh, okay.
Like I was reading it
Differently.
Yeah.
Okay. Yeah, usually when we talk about any of these, like the algebra of functions or the composition of functions, these two sections, I like to think of them as machines and what I'm feeding into my machine versus what I'm getting out of my machine. And then what do I do with my output? Where am I going to put it? And when we do the algebra of functions, we're not really running it through the machine more than once. So when we do compositive functions, we are, because we're putting something through it, and then we're going to put it through either the same machine or we're going to put it through a different machine and see what else we get out. We're going to do another example, another set of examples with slightly harder functions. Because let's have fun with it, why not? And this time they're going to start asking us to find the domains. F of g of x. So this time our f of x function is the square root of x, and our g of x function is x minus 3. Remember back from Wednesday or from 2.2 The domain of any function is negative infinity to positive infinity, except for two special cases. One, if you have a variable under your radical, or two, if you have your variable in the denominator of a fraction. Those are the only two times where you come up with these trouble spots. So the stuff that we learned in 2.2 really does come back to play here whenever we start finding the domain. But first we're going to find f of g of x. So I'm going to take g of x and I'm going to plug it into my f of x. Well, f of x is the square root of x, but now I'm going to put in g of x instead. So I get the square root of x minus 3. That's it. Can't do anything else with it. But then I've got to find the domain. So I'm going to move this out of the way so you can just see this. So in order to find the domain of f of g, first I'm going to consider the domain of f. So what is the domain of our f of x function? What values are we allowed to put into this function?
Greater than or equal to 0.
Yeah, anything that's greater than or equal to 0. So I'm going to write that as an interval. Domain of f is usually, I just write a little f to the side so I know what it is. The domain of f can be 0 or anything greater than 0. So 0 is our lower limit. Absolutely fabulous. Good job. Okay. What about g? Do we have any trouble with g? What's the domain of g?
Negative infinity to positive infinity.
Yeah, there's no problems with g. G plays nice. We're good there. But we need to find the domain of f of g. So what would be, if we were looking at at our f of g, where are we going to have problems? How do we find that? Like, what don't we want to happen underneath our radical? Right, we don't want it to be negative. So we want this x minus 3 to be greater than or equal to 0. That's what we want. So let's solve it and figure out what x values cause problems. So x has to be greater than or equal to 3. As long as x is greater than or equal to 3, we have no trouble spots. So what I need to make sure is that this is written then as 3, infinity. Are all of those points, or all of these x values, are they in my domain of f? Yeah. So we don't have to do anything else actually. So sometimes we are able just to look at what our new function is that we created and we don't have to worry about anything and we're good to go. Other times, like here in a few minutes, we're going to have to remove some trouble spots, some extra trouble spots, because stuff is going to lie in our composite function that didn't lie in our original function, and then we have issues. But in this case, this is our d of f of g. We don't have to make it any harder than it actually is. Let's look at g of f of x. So I'm going to take the function of f and stick it inside the function of g. Well, g was the x minus 3, but instead of x, I have to write the square root of x, and then I still have the minus 3. Again, a lot of times making the composite function itself isn't super difficult, regardless of what the composite functions look like. There's nothing else I can do with that, so that is the composite function. So if I'm looking at this composite function, who wants to tell me what the domain is? All numbers greater than or equal to 0. Yeah, because we still can't have negative numbers underneath our radical. So all numbers greater than or equal to 0. you're going to see where we have to do a little bit more to find our domain in the next examples. And you can't see anything. There we go. F of x is 1 over x minus 2. G of x is 5 over x. I'm just writing the same thing a little bit bigger so you can see it. And the first thing that they're going to want us to find is f of g of x. See, like I said, fractions are your friend. And if they're not, you need to become friends. I'm going to take my g of x function and shove that baby inside of my f of x function. 1 over, and then instead of x, I'm going to stick in 5 over x. So I have a fraction inside of a fraction, and everybody goes, gross. What do we do if we have a fraction and a fraction? Yeah, we're going to have to rationalize that denominator real bad. So I want what's in the bottom to have like a common denominator. So I'm going to multiply the top and bottom of my 2 by x so that I can join it together. I'm kind of ignoring this top part and just treating this bottom part like it's all one big thing on its own. So that I have 5 minus 2x all over x. Now what I really have is I have 1 divided by a fraction. And when you divide by a fraction, what we actually do is we flip it and multiply it. So this becomes x over 5 minus 2x. We just flip it and bring it back up to the top. Here's what I did. I have 1 divided by 5 minus 2x over x. That's what this all says. It says this. But I switch that to multiplication and I flip the second fraction. And that gives me what I have over here. Again, if fractions are not your deal, on my YouTube site, Math 20, Chapter 1, Section 3 is where we deal with a lot of the fraction rules. It's not a bad one to go watch. But now we need to figure out where all of our trouble spots are, because we're definitely going to have a few trouble spots here. Sorry, I'm trying to get my papers all organized. They're all flipped. Because if I look at this right now, as it is there any trouble spots?
Yes.
Where?
The denominator is x.
Yep, and the denominator is an x. And what do we not want to happen in the denominator?
0 or less.
Yeah, we don't want to have this. We can have it less than 0. We just don't want it to be 0 because we can't divide by 0. So we need 5 minus 2x, which is the denominator. We need it to not equal 0. So we're going to figure out where it does equal 0 because that's the problem. So I'm going to subtract that 5 over and divide both sides by the negative 2, giving me 5 halves. So when x equals 5 halves in this composite function, we have issues. But we need to think, was that included in our original, like were there any trouble spots in our original functions? Because if there were, we have to get rid of those things too. Because the definition of the domain is we have to take the domain of G and intersect that with our composite domain to actually find the domain. But x has to be in G. Like, we have all this stuff we've got to do. So we've got to look at all of our original domains as well. So look at the original domain for f. Remember, f is 1 over x minus 2. So we don't want that x minus 2 to go to 0 for the domain of f. That would be a problem. Where does that happen? That happens when x is 2. So the domain of f would have been negative infinity to 2 union 2 to infinity. Okay, what about the domain of g? What is it? Right, it just can't be 0 because g was 5 over x. So we can't have x equals 0, so we would write that as negative infinity to 0, union 0 to positive infinity. So we've got all these different things going on, but we need to find what is the actual domain of the entire function. Well, according to our rule, back here, the domain of g intersect with the domain of f of g. Domain of g intersect with the domain of f of g, which I didn't write out. So how would I write where we don't want x to equal 5/2? How would I write that out as an interval? If I look at how I wrote out x can't equal 0, and I wrote it out like this, how would I write out that x can't equal 5/2? Okay, well, I'm not looking to combine them yet. I'm just asking strictly for right here, for just this. Don't worry about combining them. I have x can't equal 5/2. How do I write that? Yeah. So it's exactly like the one with 0, only it's dealing with 5/2. So in order to find the actual domain of this composite function, I need this to intersect with this. Okay? But to lie in the intersection, that means all your points have to lie in both. Well, what point did we cut out of our domain of g? We cut out the point in 0. So that means it can't lie in the composite function. But what point did we have to cut out here? We had to cut out 5/2. So those we have to cut out both of them. Okay? We can't have either one of those because we can't have it, if it's not here, it can't be here. If we don't run it through our machine in the beginning, we can't get it out at the end. Like, there's no way to get it there. So since we're not plugging 0 in, we can't get it back out. And we don't want to run 5/2 through because it's going to break our machine. So that's basically what's going on. So we have to write one really long interval where we start at negative infinity, because they both had that in common, so that's good. And then we go until we hit what I call the first trouble spot. So which one's bigger, 5/2 or 0? Or which one's smaller, I guess is the way to think of it. 0 is smaller, so we're going to hit it first. Then we're going to skip it. We don't want 0, we can't put it in our machine, it's going to break our machine. So we're going to skip over 0, and then we're going to move right along until we hit our next trouble spot, which is at 5/2. And then we're going to skip over 5/2 and go on for forever because those are our 2 trouble spots, and those are the ones that are going to break our machine if we try to put them through there.
Can it not equal negative or positive 2 as well, since it would be a trouble in the first function?
In the first function, that's in f of x. And the problem isn't so much that it's in f of x, it's whether or not our g of x's lie in our f of x. Because we're sticking our g of x's into our f of x. If we flipped it, then it would be a different situation. I know that this is confusing. I know that this is hard for this one, which is also why you can guarantee I'm not going to stick one quite that hard on a test. Okay? This is like the extreme situation that you would have. Okay? Let's do one that's slightly nicer. Same functions. So I'll put the functions back up there. F of x and g of x. Let's find g of f of x. Ugh, I keep doing this. g of f of x. So we're going to take our f of x function and plug that baby into our g of x function. So we have 5 over x, but instead of x, we're going to put our f of x. So again, we have a fraction and a fraction. But what this says is we have 5 divided by 1 over x minus 2. So flip the second one and change it to multiplication. So what we're really saying with this huge, gross, complex fraction of 5 divided by 1 divided by x minus 2, we're saying 5 times x minus 2. So we get 5x minus 10. Now, when we get the answer, we're like, oh, well, that's nice. There's no problems then in our domain. Not quite. We don't want to look at the answer every time necessarily. We want to look at anywhere along the problem. Did we have a problem spot? Because what happens is I stuck my f of g, my function f of x into my g of x function. And the output didn't cause any problems. But what I initially stuck in was my f of x function. Was there any trouble spots in f of x that I'm not going to actually run through my g function? Is there anything I'm not running in there? Huh? 2. If I had 2 in my f of x function, it causes a problem. So 2 didn't lie in the domain of f. And if 2 doesn't lie in the domain of f, then I can't run it through my machine, which means it can't lie in the domain of g of f. Okay? So that's the only spot I have to take out, because I can't run it through that machine. And there's no new problems with this function. There's no new ones that come out. Do you see that? Our last one, let me show you. Our last one, we took g of x. Let's see, where can you see? We took our g of x function, which had a trouble spot at 0. And we plugged it into our f of x function. And then we got out this huge thing right here. But our answer has its own trouble spot. So we had a trouble spot here. It was the 0. And then we found a new trouble spot at 5/2. And that's why our domain had to eliminate both of those. Does that make more sense? Sometimes looking at, I think this one's a little bit easier and helps explain that. This had a trouble spot, so we have to take it out of our composite function domain. But our composite function didn't have a trouble spot. So we only have to remove that one spot. So the only trouble spot is that 2 from our original f of x function. Yeah. There. Is that a little clearer seeing it with the slightly simpler problem on how we found the domain? Because if the original function that we're dealing with has that trouble spot, then we're not running it through the machine. So that one's already been taken out. And then if the new function that we've made at the end has a trouble spot, we take it out as well. That's really what it comes down to. Okay. So this section is called composite functions. We take a function, we shove it into another function. If you think of the word composite or composing, is there an alternative, like an opposite to the word compose? Decompose. You can decompose functions. And I'll go ahead and tell you straight out of the bat, we don't do much with these. Why? Because you can get more than one right answer, and as a mathematician, we don't like that. So I think you have like 2 or 3 on your homework. You will have like 1 on your quiz of these. And there's no notes for it. You're just going to see it. And it says if h of x equals 2x minus 3 to the fifth, we need to find a function f of x and a function g of x so that h of x is a composition function. And I'm going to show you a neat little trick, and that's really about as much as you need to know. Actually, I guess I have two of them because there's two little tricks. So instead of shoving a function into another function like we've been doing, we're looking at this one function thinking, okay, well, what two functions did we shove together? And I will tell you, almost all of them will look like this, where you have something, some expression raised to a power, or you have a fraction with something in the denominator, or you have a radical with something under the radical. And that is supposed to really direct your eyes to what we can do. Because here's what I'm going to show you. If we have, I'm going to rewrite the h of x. And there is more than one right answer. That's why we're not going to do many of these. So notice we have a set of parentheses, and inside the parentheses we have an expression. Do you see that? So I'm going to let that expression be a function. I'm going to let that be my g of x function. Because to me, it looks like I shoved a function inside of another function right there. I just shoved it in. And if I shoved that g of x in there, that 2x minus 3, if I shoved that in, what was the thing that I shoved it into? Yeah, x. That's my f of x function, which is what?
X to the fifth.
Yeah, x to the fifth. All of this becomes my f of x function. Keep it simple is what I'm going to tell you. Could you make it harder and say, well, I'm going to let g of x be 2x, and I'm going to let this, my f of x, be x minus 3 to the fifth? Sure, but that's a little bit more complicated than just seeing, oh, wait, it looks like I shoved something in here. What if I take that out and put an x in that place? What is it? So keep it simple, because like I said, you're not going to do very many of these. They will all look like this, or they will have like a radical with 2x minus 3, like that, or it'll be like this last example where we're going to decompose h of x equals 1 over x plus 3 to the third. And if I decompose this h of x, what do you want your g of x, the one that we shoved in, what do you want it to be in this case?
X plus 3.
Yeah, let's let that baby be x plus 3. And if that's x plus 3, then my f of x would be what?
1 over x to the third.
That's exactly right. Keep those simple. Like I said, there's 2 or 3 of them on the homework. That is it. You won't be asked to find the domains of these decomposing functions or anything like that. That is literally the extent that you will do with them.